Okay, so in this video, we're just going to review differentiation and integration of just logs. Because like I said, once again, when we get into a lot of this uh, integration techniques, you're going to be seeing e to the x, you're going to be seeing a lot of ln of x, or just logs in general. So I think it's easier for this if I just kind of give you the formula first for the derivative of the natural log of x. So the derivative of the ln of x, I guess I don't need these parentheses, is equal to 1 over x. Now, remember, this right here is called the argument. All right? So, initially, the way that we look at this is the derivative of the natural log of x equals 1 over x. Now, the reason why, okay, is if we want to prove this, we're going to let y equal the natural log of x. Now, we know from algebra that there's a relationship between logs and its inverse, which are going to be exponentials. So e to the y equals x. That's just that's our basic definition there. So we're going to differentiate this equation implicitly. So use implicit. Hopefully I spelled that right. Differentiation, okay, with respect to x. So what's going to end up happening here is on the left-hand side, we're going to get e to the y times dy dx. Remember, this over here is a chain rule, all right? And then on the right-hand side, you just get 1. And so, oops. So solving this for dy dx, we get dy dx equals 1 over e to the y, but we know from up above, e to the y is equal to x. So dy dx is equal to 1 over x, which is exactly what we said all the way back up here. So it's a really easy proof when you think about it. Just like if I want to go back here real quick, the proof, and maybe I should have wrote that up here, and I didn't. That's my fault. Here we go. All right. Proving the exponential e to the x, its derivative is e to the x, is really simple. If you're going to take a step and you got to think about, okay, like how do I apply what I've learned, these definitions to this type of problem here, okay? So that's pretty nice. Now, as always, this is a special case, so let's give you the general case. All right, this is my favorite. The general cases are always my favorite because they work on everything, not just something specific. So, if I wanted to find the derivative of the natural log of u, that is going to equal 1 over u times du dx. Remember, the argument here, you're going to have to use that chain rule to differentiate this. So it's 1 over u times du dx. A really simple example on the right-hand side would be d dx of the natural log of, let's say, 3x. Well, according to what we have on the left-hand side, it's going to be 1 over 3x times the derivative of 3x, which is 3. So this is going to be 3 over 3x, which equals 1 over x. Now, another simple example would be something like find the derivative of the natural log of sine x. Now, in this case, you're still going to apply the rule above, so it's going to be 1 over sine of x times, but now you need the derivative of sine, which is cosine. And that's going to give you cosine of x over sine of x, which we know as cotangent of x. All right, now, this next example, I'm going to do 2 ways. And the reason why I'm doing this is because I want you to make sure that you don't forget all these little things, all right? So let's go ahead and let's find the derivative for the natural log of x plus 1 over the square root of x plus 2. Okay? So, let's take our time with this. Let's make sure we walk through this together. This is going to equal 1 over x plus 1 over the square root of x plus 2 times the derivative of x plus 1 over the square root of x plus 2. This is nothing more than just, remember, this is our argument here. So that's u, so it's 1 over u times du over dx. It's derivative of u with respect to x. So that's all I did here. But as you can see, this is going to get very, very messy very, very quickly. And the reason why that is true, the reason why this is true is because first, I'm going to use my highlighter here. First, you have this right here. Now, that's not too bad. All right, that's just 1 over 1 divided by x plus 1 over the square root of x plus 2. So it's just multiplying by the reciprocal. That's nice. However, this right here, this is going to get very messy very quickly because you need to use the quotient rule for this. So you can see it gets really messy really fast. But that's okay. We're just going to go ahead and we're going to do it. Oops. Don't know what happened there. There we go. All right. So let's multiply by that reciprocal. That's done. Now we're going to multiply this by the quotient rule. So it is the square root of x plus 2 times 1 minus the quantity x plus 1 times 1/2 times x plus 2 to the negative 1/2 all over x plus 2. Once again, like I said, it gets really ugly very quickly, but we can go ahead. We can kind of simplify this a little bit. So I'm going to clean this up a lot because we're going to put brackets around there, and we're going to go ahead and we're going to distribute. So in our denominator, we get x plus 1 times x plus 2. In the numerator, when I distribute there, I get x plus 2. And then when I distribute all the way over here, okay, that's going to be, and I'm going to write it off to the right. So it's x plus 2 to the 1/2 power times x plus 2 to the negative 1/2 power. Now remember, order doesn't matter when you multiply. That's a commutative property, okay? So I can take the square root of x plus 2 and multiply it by the square root, or I'm sorry, multiply it by the quantity x plus 2 to the negative 1/2 power. So 1/2 plus negative 1/2 is 0. So this whole thing just goes to 1. So I'm left over with minus 1/2 times x plus 1. All right? Let me just erase this real quick. Let me do that. There we go. All right, so here I'm just going to distribute. We get negative 1/2 x minus 1/2 plus x plus 2 all over x plus 1 times the quantity x plus 2. And that's going to give us, let's see, negative 1/2 x plus x is going to be 1/2 x. Negative 1/2 plus 2 is plus 3 over 2 all over x plus 1 times x plus 2, which I can factor out a 1/2 to say 1/2 times x plus 3 all over x plus 1 times x plus 2. Or just simply x plus 3 over 2 times x plus 1 times x plus 2. Okay, so like I said, you can see how messy this gets. The other approach would be something like this. The other approach would be, before you just dive right in and start doing your derivative, why not just apply your rules for logs and say, well, we're going to take the derivative of the natural log of x plus 1 minus the natural log of the square root of x plus 2, which, once again, using a little bit more rules here, we're going to get the natural log, or the derivative of the natural log of x plus 1 minus 1/2 times the natural log of x plus 2, because remember, x plus 2, or the square root of x plus 2, is really the quantity x plus 2 to the 1/2 power, and I can pull that log out front. So from here, we have our first derivative, so we'll do this one first, which is going to be 1 over x plus 1 times the derivative of x plus 1, which is 1, minus 1/2 times the derivative of the natural log of x plus 2, which would be 1 over x plus 2 times the derivative of x plus 2, which is 1. And this gives us 1 over x plus 1 minus 1 over 2 times x plus 2. And then finding a common denominator and everything like that, you will end up getting, in our denominator will be 2 times x plus 1 times x plus 2. And then in the numerator, you get 2 times x plus 2 minus the quantity, x plus 1. And that's going to give us 2x plus 4 minus x minus 1 all over 2 times the quantity, x plus 1, times the quantity, x plus 2. And finally, 2x minus x is x. 4 minus 1 is positive 3 all over our denominator, and it's the same exact answer. So when you approach logarithmic problems, sometimes it's in your best interest to take a step back and say, can I rewrite this to make it look a little bit easier for us? We're going to be doing a lot of that when we talk about partial fraction decomposition and everything. So let's talk about integrating the natural log, all right? Or better yet, integrating when the natural log is the answer. We need, in order for us to integrate the natural log of x dx, we need a technique called integration by parts, which is going to be in the next chapter. So can't really do this one yet, but if you recall the basic power rule, it was the integral of x to the n dx equals 1 over n plus 1 times x to the n plus 1 plus c. But there was always a little thing attached to this, which was n cannot equal -1. So the big question becomes, how do you integrate this? Because in this situation, if you rewrite this using the power rule, or I'm sorry, if you rewrite this using the negative exponent rule, we get x to the -1, which completely violates this definition here. Well, to think about this, we need to go back to derivatives. So, if we wanted to find the derivative if f of x equals the natural log of the absolute value of x, and remember, technically, the absolute value of x, or I'm sorry, when you have a natural log, you got to make sure that the argument is positive. That's why we have the absolute value. Okay? And also, remember the definition of what the absolute value really is. So, and before I even write this down, I, I know some of you may be thinking the absolute value definition is it's always positive, and that technically is correct, but it is not a good way to think about what the absolute value is. The absolute value of x is defined as x if x is greater than 0 and negative x if x is less than 0, and that is because the absolute value measures a distance away from 0. See, distances are never negative, all right? The absolute value, I agree, the answer is always going to be positive, but now you got to understand why. And it's because this is the algebraic definition of what the absolute value is. So if this is the case, then f of x, which is defined as the natural log of x, is going to equal the natural log of x if x is greater than 0, and the natural log of negative x if x is less than 0. Because if x is less than 0, say negative 2, you're gonna have a negative 2, which is really positive 2. All right. So the derivative of f of x, which equals the natural log of the absolute value of x, is f prime of x equals the derivative of each one of these pieces up above, this piecewise defined function right here. So put a little red box around it. We're going to differentiate each piece. So it's going to be 1 over x if x is greater than 0, and then 1 over negative x times negative 1, remember chain rule, which is 1 over x again if x is less than 0. Therefore, the derivative of f of x is equal to 1 over x for all x not equal to 0. Because remember, if x is equal to 0, this thing is undefined anyways. All right? So our derivative of the natural log of the absolute value of x equals 1 over x, which we kind of already went over earlier. Okay? So now the corresponding integration, the integral of 1 over x dx, is equal to the natural log of the absolute value of x plus c. And I got that by just looking on the left-hand side and just integrating both of these sides. So I'll go ahead and do a real easy example real quick. Let's go ahead, let's integrate from 1 to e the ln of x over x dx. Now in this case, we're going to have to use u substitution. So we're going to let u equal the natural log of x. Du, therefore, is going to equal 1 over x dx, which is exactly what we want. Because if you look at this, I'm going to write it in blue. But if we rewrite this as the integral from 1 to e, I can rewrite this as the natural log of x times 1 over x dx. And right here is my du. Okay? So let's go ahead and we're going to make our substitutions. So the integral from 1 to e of the ln of x over x dx is going to equal the integral. We'll worry about the limits of integration in a second. It'll be the integral of u du. And now for our limits of integration, I'll do them in red. I'm just going to erase this real quick. Remember, the ln of 1, which is our lower limit, is equal to 0. And the ln of e, by definition, is equal to 1. So it's going to be the integral from 0 to 1 of u du, which when we integrate this, we're going to get u to the second over 2 between 0 and 1, which is equal to 1/2. So I hope this helped kind of refresh your memories, and if you've never seen this before, now you understand why these are the way that they are. All right, I will see you in the next video.